Hello and welcome to this video. Today we're going to go through Thevenin equivalent circuits. So today I want to show you basically what it is and then how we obtain this circuit as well. So to start, let's go ahead and look at a circuit here. So in this sketch I've got a bunch of resistors, we've got a couple independent voltage sources and a couple independent current sources inside this dashed boundary box. And these are hooked up to terminals A and B. So the basic idea of the Thevenin equivalent is we don't care about what's inside this dashed box. We only care about what comes out at terminals A and B, because that's where we're going to hook up whatever it is we're plugging into this circuit. So that's all that we care about. So really we want to simplify all these circuit elements inside the box into one independent voltage source and one resistor. So this is given by the Thevenin equivalent circuit, which is here, where we have one voltage source, like I said, and then one resistor, and they're denoted VTH and RTH for Thevenin. And then we have a current that goes through this circuit, which is the Norton current. And this is what we're going to try and find today through an example. So I'm going to walk you through the step-by-step process. And with that, let's go ahead and explain what the process is. So essentially there's like 5 steps to this. So the first step will be to find our voltage across terminals A to B with the terminals AB left open. And then we're going to do it again with them connected by an ideal wire. And then that way we can find the current, which will be our short circuit current, or the Norton current. And then the fourth step will be to calculate the Thevenin resistance after that. And then finally we're going to use this to draw our Thevenin equivalent circuit. So let's go ahead and get started with the example. So for step 1, we need to find the voltage across AB with the terminals AB left open. So as you can see, there is no wire connecting these two terminals here, completely left open. And we know that we have to define a ground. So we've got our ground shown here in blue, and this is where the voltage is equal to 0. And that means that we know the voltage at terminal B because it's directly connected. So then VB is equal to 0. And then I'm going to define my node, which is V1 in red. And this is essentially equal to A, because since these two are not connected, there's no wire connecting these, there's no current flowing through the second resistor, which means that there's no voltage drop. So therefore, V1 is actually equal to VA. And the nice thing about this is since our ground is directly connected to node B, or terminal B, and then V1 is equal to VA, that means V1 is actually equal to VAB, which is the voltage across terminals A to B. Which then means that it's equal to the Thevenin equivalent, because we want to find the voltage across the two terminals. So with that, let's go ahead and use the node voltage equation to go ahead and get started solving. So here I've got my equation written out with all 3 branches of current that will be coming out of node V1. So for the first branch, we'll have it going down this way. And so this is this one here, where we have V1 minus our 10 volts divided by the 3 ohms, which is the resistance 1, which is shown over here. And then the second branch, which will be here, is coming in, because I have this current source coming into it, into node V1, so therefore I'm assuming it's negative, because I'm using sign convention where any current coming into the node is negative, any current coming out of the node is positive, like this. And you can use the other sign convention too, so if you have your signs flipped, it should work out just the same, because you would just divide the whole thing by -1, and thus your sign convention would change. So it really doesn't matter, but that's the one I'm going to use. And then the last branch, since there's no current going through this one, we just need the one here. And that'll be V1 minus 0 because it's directly hooked up to ground. There's no voltage source in between there. And divided by 12 volts is equal to 0. And so now I'm multiplying by 12 the entire equation because that's my largest denominator, and I'd like to get rid of all the fractions if I can because it makes it easier for me to solve. So with doing that, I distribute the 12 ohms through to each term. So if we go to 1, this will spit out that we have 4 V1 and 40 volts. And then if I multiply again by the 2 amps, we get negative 24 volts, because amps times ohms is volts. And then the 12 cancel with this 12 here, so we're just left with the V1. And then if I collect my like terms, you'll eventually get down to that V1 is equal to 64 over 5 volts. And this is equal to VA, which is equal to our VTH. So we're going to take that, we're going to save it for later, because we need to go on to the next step now, which is to find the voltage again, but this time we need to connect terminals A and B And the reason we have to do this is so we can get our short circuit current, which here is shown in blue. So to get that, we're going to do the same thing, node voltage method again, but do note this is in blue. The reason it's in blue is because it's a different voltage now. We have added an extra current in an extra branch. So therefore, it's going to change the voltage at that node. So that's why we have to redo everything. So with that said, let's go ahead and write out the equation, which I've got here below. So I'm going to go back to green, and then this will be our first branch again, in which we're going out this way, where we have V1 minus our 10 volts, because we're going from plus to minus, so we're dropping across the voltage source, and then divided by our 3 ohms, which is our R1, given over here. And then the next branch again is our negative 2 ohms, 2 amps, which I'm assuming is coming in, so therefore I'm assuming it's negative, because it's absorbing. And then the third branch will go down this way, where we have our V1 divided by, or minus 0, because it's directly hooked up to ground, with no voltage drops in between there, and then divided by our 12 ohms. Then finally our last branch, which is the new branch that we have just added because we have shorted this circuit like so. That means we have V1 minus 0 over 5 ohms. And then again multiplying through each term by 12 ohms because that's my largest denominator, and I want to remove all the fractions because it makes it easier for me to solve. That'll give us a few different terms, so we'll have 4V1 again, 40 volts again, and then we'll get our negative 24 volts again. And then this one will cancel, so we're just left with V1. And then now the new one, which is 12 divided by 5 ohms, which will be times V1. And if we go ahead and collect like terms, we'll find that this V1 is equal to 64 or 7.54 volts, which is equal to 8.65 volts. So now what we're going to do is go to step 3. And with that, step 3 is to find the short circuit current in which is going through that ideal wire. So we need to find the current ISC, which is going through that blue wire. But now that we know that the voltage, we can use the node voltage equation to write an equation for the short circuit current. And if we notice, so this current goes through this branch like so, which means that this was the branch 4 that we used, that went through here. And so this is equal to the short circuit current. So now that we found V1, we can go ahead and plug that in down here and solve for the short circuit current, like so. So we come out with 1.73 amps, having plugged in our V1 over here, and then just solving. Then the fourth step, we need to find RTH, or the Thevenin resistance. And we're going to use Ohm's law for this, where Ohm's law is voltage is equal to the current times the resistance. And since we use, in this one, we're using VTH, so remember we found that in step 1. So that's why we need to hold on to that and bring it down. And that is equal to 12.8 volts if you divide the 64 by 5. And then once we plug this into our equation with our now found short circuit current, we can go ahead and solve for our Thevenin resistance, which comes out to be 7.4 ohms over here. And then I want to point out these equations over here on the right for you. These will be useful because these are essentially how you can relate a Norton equivalent and a Thevenin equivalent. And with that, we're not going to cover the Norton current or the Norton equivalent today, but I'll go through that in the future. But basically, the Thevenin resistance, RTH, is equal to the Norton resistance, RN. And then we have Ohm's law again, which is the VTH is equal to our Norton current times our Thevenin resistance. And then you can derive from this one, you can derive that the Norton current is VTH over RTH, or you can derive that RTH is equal to VTH over IN or I short circuit. So with that said, those are some useful equations that will help you kind of go interchangeably between the 3 different values. And then let's go ahead and write our final answer. So now we know the Norton current, we know the RTH, we know the VTH, we can go ahead and write our Thevenin equivalent circuit, which is shown in this box here, where the Thevenin equivalent voltage is 12.8 volts, and then that is in series with our Thevenin resistance of 7.4 ohms, where we have our Norton current, which is 1.73 amps going through it. And then that is our final answer. Now before you go, I want to check the answer and show you another way to find RTH, because if you're asked just to find the Thevenin resistance, there's a much easier method than going through all of these various steps. So in this case, what we can do is we can take our independent voltage sources and change them into ideal wires, and then take the independent current sources and then turn them into open terminals. And this does not work if you have dependent sources. So these are defined as, if they're in a diamond shape, it doesn't work. If they're independent, so like circular, works. So that's the ones we want. So again, I've pasted the circuit that we started with down here. We got our resistance values again. Same one as before. Now we're going to go ahead and apply these rules. So we're changing this 10 volts voltage source into an ideal wire, shown down below, and then we're going to change our 2 amp current source into an open circuit, or excuse me, like an open branch, so no current can go through it. So essentially we're just turning them off. And now we can use the resistors in series and parallel to go ahead and solve for the equivalent resistance. And this equivalent resistance will be equal to RTH. So this is a nice way to check your answer and also to just get the RTH value if that's all you need. So going through this, we can solve that resistance 1 and 3 are in parallel. So 1 over R13 is just me denoting that I'm combining 1 and 3. You can denote it however you'd like. But then this is equal to 1 over the first resistance plus 1 over the third resistance, which is 1 over 3 ohms plus 1 over 12 ohms. Grabbing values from here for 12 and this one for 3. Plugging them in here. Then go ahead and solving, we find that 1 over R13 is 5 over 12 ohms, and if we flip that, so we get R13, we have 12 over 5 ohms. Now we can go ahead and plug this into our next circuit because it is simplifying this, and we find that R13 and R2 are in series. So then the equivalent resistance is just the summation of the resistors in series. So in that case, we have 12 over 5 ohms for R13 we just found, and then we have again 5 ohms for R2, which is from up here. And then if we go ahead and add those together, we do in fact get the same answer of 7.4 ohms, which is equal to our Thevenin resistance. So again, this is just a great way you can check your answer for if you've gotten the correct Thevenin equivalent circuit, or if you're just looking for the Thevenin resistance just itself, this will be a faster way for you to go ahead and do that if you have only independent sources.